So the first thing I want to look into here is, okay, so the force, we're going to treat the sun as infinitely massive compared to the planet. Jupiter's mass is somewhat less than 0.1% of the solar mass, and everybody else is smaller than that. So it's a pretty good approximation that the sun basically sits there. But strictly speaking, both are going around the common center of mass of the sun-planet system. It's just that the sun doesn't have to do much moving because it's so much more massive. So the gravitational force is directed along the radial line back toward the sun. We saw last time the definition of torque, and that is that torque is the product of the distance from the axis that you have picked to the point of application of the force multiplied by the perpendicular component of the force. But there is no perpendicular component of the force. It's directed exactly along the radial line, and so the torque is zero. And as we will be exploring, what changes angular momentum is torque. If the torque is zero, then the angular momentum of the planet is a constant of the motion. And whenever you can find a constant of the motion, that really is going to simplify the analysis. So the angular momentum, well, we had the definition L was equal to I omega, which was equal to mr squared times omega, or times d theta dt, same thing. And that's a constant. Okay, one dot. Time derivative of theta. What's theta? Well, as indicated in the figure, theta is the angle. And we're just going to orient our coordinate system from this point here. So this is the point where the planet is closest to the sun, and that goes by the name of perihelion. And the far point over here, the one where the planet is as far away as it's going to get, is called aphelion. Just a little nomenclature. So once upon a time, I did ask what was the semi-major axis, and now I have an ellipse there, so we can actually go looky. Okay, so the semi-major axis is half of the major axis, which means that it's this distance here. And this A is customary and not to be confused with acceleration. That's just the length, the distance from the center of the ellipse out to the farthest point away from the center of the ellipse. Okay, and the semi-minor axis would be that distance there. So I don't know what geometry they're teaching in the schools these days. Have you ever traced an ellipse? How do you do it? Don't you put the two thumbtacks in and you put a string around and then you pull the, yeah. So that's what's going on here. D1 and D2 are the distances from the two foci out to any point on the ellipse. And if I add those two together, I'm going to claim that I ought to get twice the semi-major axis. Do you buy it? So I only have like one easy place to check, and that would be along the major axis here. So I have a distance to the left. So imagine that my planet is over here. So I have to go out from the sun, that's D1, and then I have to go all the way back to the other focus, that's D2. But this distance on this side that I have to cover twice, once out and once back, is exactly equal to this distance on that side. So if I add those both together, I'm going to get just the full the full length across the ellipse, 2a. And an ellipse has this property that the sum of the distances to the two foci is a constant. Okay, there's another parameter that describes how squished the ellipse is, and that's called eccentricity. And the focus is moved from the center of the ellipse a distance a, the semi-major axis, times this dimensionless number, the eccentricity, epsilon. And so for a circle, what is the eccentricity? 0. If epsilon goes to 0, this point comes back to the origin, that one's back to the origin, and the two distances d1 and d2 collapse to just the radius of the circle. Okay? So the larger the value of epsilon, the more squished the ellipse. What's the biggest we can make for epsilon? What happens when it's 1? So then it looks kind of like a line, which turns into a parabola, as it turns out, but we ain't going there. And then, just for future reference, in case you want to slingshot past the planet, if epsilon is bigger than 1, then you get a hyperbola. That's right. So these are all what are called conic sections. Today, though, we're really only going to worry about ellipses. And this is the equation of an ellipse in polar coordinates. So polar coordinates make a lot more sense for us because the gravitational force cares about the distance between the planet and the sun. And that's r. That's one of the polar coordinates. And then theta is just the angle going round. And it'll be easy to figure out maybe the period by just asking how long does it take for theta to increase by 2 pi. Okay? So if this is true, figure out what r perihelion is. Right, perihelion is there, aphelion is there. If this is the equation of the ellipse, then what is the value for r sub p? The distance between the sun and the planet at perihelion. So what angle is perihelion at? Perihelion's closest, that's where I have to have, the top is just a constant, so I have to have the biggest denominator in order to get the smallest value of r. So r for perihelion should be when cosine theta is 1. So that means a times 1 minus epsilon squared over 1 plus epsilon. Can I simplify that? To what? Okay, so this is 1 plus times 1 minus. The pluses go out, and so this looks like a times 1 minus epsilon. And that hopefully corresponds to just what we have up on the figure, and I think it does. And you can easily show that at aphelion, instead of 1 plus, what's the smallest value for cosine theta? Negative. Yeah. Slap yourself if you said 0. Thank you, okay? In my universe, cosine goes between -1 and 1. And if in your universe it goes down to 0, you live in a strange universe. All right, so a times 1 plus epsilon.